QCD and EA are considered simple, but I'll bet that the many-body physics is pretty interesting in cold QCD also. So I think we'll have more stuff to celebrate. Thank you.
Thank you, Barbara. The talk's open for questions. We have time for 2 or 3.
Is there a Stokes kind of relationship between the diffusion coefficient and the viscosity? Which one might be more?
Yeah, I can repeat the question. It was, is there a Stokes relationship between the diffusion coefficient and the viscosity? I believe the answer is yes, because of the success of hydrodynamics. You heard yesterday about some of the second-order hydrodynamics, and that actually works pretty well.
Very nice talk. Although I'm totally a non-specialist, I have a question about one of the earlier transparencies where you showed eta by S as a function of temperature for various systems. Now, what we know is that for cold atoms, there's a high degree of control.
Yes.
So I was wondering, I know that your error bars are large at this point, but to what extent would you compare the degrees of control that you can achieve in a QGD?
Well, the control is different. Of course, the cold atoms, as my AMO friends like to poke me about all the time, you do have much more careful control of your system size, system shape, not so much. It starts out spherical and then it expands when you let it go. And guess what? It actually undergoes the same kind of elliptic flow. But you have a higher level of control in the temperatures and so on. You can dial the interaction. In our case, we can't dial the interaction, but we do absolutely, after all, know the Lagrangian for the interaction. And we do have more particles. It's pretty tough to capture thousands of particles in a nice cold atom system. So I think they're actually pretty complementary to one another.
Excellent. But the string theory bound also should have an error bar, right? Because you go to next leading order in 1 over n. But I don't know if that has been calculated.
I think so too, but I'm going to toss that question at the string theorists.
I don't think this is the expansion parameter. Great talk. I wanted to ask you about your data. Slide 10 you showed fits to the diffusion coefficient for a variety of models.
Right.
And the chi-square per degree of freedom seemed to be rather high. So I wondered if your uncertainties have been overestimated.
Yes. Very good question. Get to slide 10. Almost there.
Yeah, thanks. Yeah.
Right.
Well, good enough to quote them below. That's how that certainly looks like either the uncertainties are correlated between bits, so
yes.
You need the covariance.
Right. No, that's so. Where do the uncertainties come from in all of these different models? Some of them use the same hydrodynamic expansion of the system. That's a very important ingredient, of course, if you're looking for the many-body interactions. And that's decreasing as a function of time because the density goes down. And that expansion is, for a while anyway, ballistic. They don't all use the same one, so some of the differences come from that. There are quite some differences in the ratio, or even how well they model multiple scattering of the heavy quarks, plus how they model the medium that the scattering is with differs. Again, not all of them model the gluon radiation the same and the ratio between them. So, why are the chi-squareds not better? I think there's still too many dials in the models that are not perfectly well controlled. On the other hand, 10 years ago, we didn't have anything like this, so I think we're on the right track.
Thank you. Okay, so last question. Yeah, can I make a comment and also answer Partho's question about the error bars? So in string theory, when you add fundamental matter, the 1/4 pi pound is actually violate. It's 1/4 pi times 1 minus NF over MC, something like that. That's the structure. And it's very subtly related to the unitarity of the theory. So the leading higher derivative correction to Einstein's theory in string theory actually has a certain sign. and that is governed by unitarity. So if the 1/4 pi bound is actually true, there has to be some really subtle thing that is happening at the ultra high energies, which somehow restores the bound. So otherwise, the error bar, what is asking, actually is negative.
Okay. So I probably should draw it as a smear rather than a line.
Right.
Fair enough.
There is a
Okay.
probability expansion parameter.
So let's thank Barbara. And is Littlewood already online? Thank you, Barbara. So our next speaker is Peter Littlewood from the University of Chicago. Yeah, he is online. Hello.
Hello,
You can hear us, right?
I can hear you.
Okay, excellent. Welcome, Peter. And we are looking forward to hearing Peter Littlewood on the topic phase transitions in electron-hole plasmas, a superfluid of light. So without further ado, Peter, the floor is yours. Thank you.
So good morning, everyone. Thank you very much for inviting me to this one. I'm sorry I'm not there with you. I thought I'd just start with a few remarks, of course, about Vikash. Vikash and I met maybe some 20 years ago, not so much in the context of nuclear physics, although particle physics, I learned quite a lot about it from him. But really, with me being an administrator and him being an administrator, and building a program between Cambridge, where I was at that time, and Calcutta. So that was a small, modest idea, but actually was very successful and was important for the students. But because what I gained from that was the knowledge of Vikash himself, his generosity, his big personality, and his wonderful commitment actually to progressing science and scientists of the time. Now, I am a condensed matter physicist, but I'm going to talk about a topic which I think is runs in parallel to some issues that Vikash has been working on over many years. And that's actually the issue of superfluids. But superfluids made out of electrons and holes and photons. And that very surprising connection actually between that problem and nuclear matter. And going even further, that connection takes you all to sort of classical problems involving nonlinear dynamics and sort of long emission on longer circular systems, which actually includes models of bird flight. So let me try and take you through that in the next few minutes. I am sure you have talked a lot about this phase diagram. I stole it from a recent review article of Vikash, talking about the...
You haven't shared your screen. We don't see your slides.
You don't see the change? That's